Ionization energy is the third trend that we typically talk about with our periodic trends in AP chemistry. And I would say that this is one of the more popular things that they will ask you questions about. Radius and for ions and for your atoms is also a very popular question, but ionization energy really kind of gets to the heart of, do you understand the interactions going on between the electrons and the protons inside your atom? And so ionization energy, there are a couple different type of things that they can ask you, so we're going to go through them. The first thing you need to know is that the ionization energy is literally the energy to make something into an ion. So it's, in this case, the energy required to remove a mole of electrons from a gaseous atom. And so, like I said, what's going to end up happening is that you're going to turn it into, in this case, a cation or a positive ion, because you're taking away the electrons. What ends up happening is your ionization energies typically show up as positive numbers because you have to add energy to take an electron away. So if I want to rip an electron away, we've talked about this before, we have to add energy in the form of ultraviolet light or something along those lines. Okay? When we talk about ionization energies, they talk about them as the first, second, third, whatever type of ionization energy. And so the first ionization energy is the energy it takes to remove the first electron from your atom's mole sample that you have. If we have a second electron, then it's called the second ionization energy. So the reaction in general, when we're talking about ionization energy, is that you have for your first ionization energy, your plane element in its gas phase. Then what happens is we add energy and we take away an electron, and so what's left is X plus, and X is of course a symbol for your element, plus an electron. And that electron then is, off doing whatever, and it's not super important for us. If we talk about something like the second ionization energy, the second ionization energy starts from the point where you've already removed the first electron and you are turning your element into a +2 ion. So if you kind of see at the bottom here, when this little thing goes away, hopefully at some point in time, the X plus 1 turns into X plus 2 plus another electron when we talk about them, okay? So if we'd have a third one, it would keep on going and going and going. In general, when you see trends in ionization energy, what happens is ionization energy increases when you go from the left to the right across your period because of that increase in the effective nuclear charge. So that effective nuclear charge that we talked about is super duper important, and it keeps coming back again and again. Ionization energy decreases from the top of a family down to the bottom because of the number of electron shells and more shielding that happens. It becomes more difficult to remove every electron as you keep taking them away, and that has to do with the proton to electron ratio, which we'll get into in just a second. And then there is a large jump that happens after the valence electrons are removed, and so we'll talk about those as well. Okay, so this is the general pattern that you see for your ionization energy. And like I said, ionization energy tends to generally increase as you go from the left side of your periodic table to the right. So if we look at the second period here with lithium, beryllium, if we would put a line on that and generally trace the trend, you would see kind of an upward slope. And that's because of the increase in the effective nuclear charge. So when I talk about ionization energy, I like to talk about sheep and shepherds. And so what you have to kind of think of is the number of protons is the number of shepherds that you have, and your number of valence electrons are the sheep that you have. And so if you think about as we go across a period, when you are going across a period, all of the electrons that get added to the elements here get added to that same energy level. So I'll bring back my handy dandy sphere that we've got here, okay? So when I add my valence electrons on the outside, they all go on the same rough energy level if we are talking about elements that are in the same period, okay? But there are, and those are our sheep. So those are the sheep here. So we get more sheep, but the sheep aren't any further away. And in fact, they're pulled closer into the shepherds, which are inside my nucleus. I think of the protons as the shepherds. They get pulled in more and are easier to hold on to because the higher number of shepherds can keep the electrons closer. And so if I want to try and pick one off of there, it's more difficult. So as we go along, as we go across a period, it gets more difficult to take them away because that effective nuclear charge pulls those electrons in closer and stronger, and they're harder to remove. There are some weird exceptions that you'll see. So if we look at the second period, beryllium is 899, and then all of a sudden it takes less energy to remove the electron, that first electron from boron. And you say to yourself, the trend told me that it was going up. There's a weird thing that happens when we talk about half-filled P shells and fully filled S shells. Okay, it's not so much a thing with the fully filled P shell, but there are exceptions that happen in the fully filled S shell and the half-filled P shell. And what ends up happening is that the elements that have electrons that half fill a P shell, if you have each of your orbitals with one electron in there, it provides a certain amount of stability, kind of like we talked about with electron configuration. And if I can get an S shell that's full, that provides a little bit more stability and fewer electron repulsions. So what happens is the trend is generally that it gets harder to remove an electron as we go along, but exceptions to the trend are caused by either a half-filled shell, like nitrogen, phosphorus, and that gang, or a fully filled shell in the S shell, like in beryllium, magnesium, calcium, that kind of thing. So you see the dip down for the ionization energy in boron because boron has one electron in its p orbital, and that causes a little bit more repulsion. And so you get a slightly lower ionization energy. And then it goes back up. And then you get the half-filled nitrogen, which is really nice and stable. And then you add another electron in oxygen to the orbit, and then it destabilizes a little bit, so it's a little bit easier to take it away. So that's when you go across a period. When you go down a family, it gets easier to take the electrons away because the electron that we're talking about is just physically further away from the nucleus. So that's the sheep and shepherds again. If you think about your shepherds as your protons in the middle, if you have more layers of electrons, or sheep in this case, there is a harder time keeping track of that electron way the heck out here if you are the protons in the middle, because there's more and more electrons in between. And so it's easier to pick that electron off. So if I'm explaining that, I'm using the electron shielding argument. I would say that an electron that's many more shells away is shielded more from the influence of those protons, and so they are easier to take away. So those are the general trends that we talk about. Now, there are weird things that happen when we talk about taking a look at what we call successive ionization energies. So a successive ionization energy is going to be, what's the ionization energy of the first electron I take off, then the second, then the third, and so on and so forth. And so this table here shows your ionization energies for your different elements up to 7 electrons taken away. So you will see sodium here is 498 for its first ionization energy, and then 4,560 for its second, and then it keeps going up from there. And like I said, every time you take away an electron, it gets harder for you to remove the next electron. And I'm going to show you an example. So just let me get my dot cam up. And we'll talk about magnesium. So when we take a look at Mg, Mg has 12 protons and 12 electrons normally. And you'll have to forgive my kind of quick drawing here. But if I have 12 protons and 12 electrons, I have electrons that hang out in 3 energy levels. This is the 1s, this would be the 2s and 2p, and then this is the 3s shell. So when I talk about my successive ionization energies, my first ionization energy, which I'm going to abbreviate IE, that is when I take regular old magnesium in the gas state and I take away one electron and turn it into Mg plus and one electron. So that is that first ionization energy. And the energy to make that happen is 736 kilojoules to remove 1 mole of electrons. So if I want to take away, let's say, this electron here, I'm going to have to put in 736 kilojoules to do that, to take away 1 mole of them. My second ionization energy is going to be Mg plus turning into Mg2 plus another electron. Now, this is probably the ion that you recognize the most for magnesium, and that's because when we normally make ions, we take away both electrons so that we have this full shell underneath. The ionization energy for the second ionization of magnesium is 1,445 kilojoules per mole. So if you think about it, this takes twice as much energy. And the reason it takes twice as much energy is because when you start off trying to take off that second proton there, or the second electron, not second proton, you are taking away an electron from an atom that has 12 protons, but only 11 electrons. And so because there is an imbalance in this first one, where we have, this first one is 12 protons to 12 electrons. The second one is 12 protons to 11 electrons. So it's harder to take away the second one because you have more protons pulling in on fewer electrons. Okay? Now, the third ionization energy for magnesium is going from magnesium 2 plus to magnesium 3 plus an electron. Now, this is a weird thing. I'm guessing you probably never saw magnesium 3 plus, and that's because normally we just lose those 2 electrons. So magnesium 2 plus to 3 plus means that I am taking away an electron from a full shell that is 1 whole energy level closer to my nucleus. So not only am I taking away an electron, because my ratio is 12 protons to 10 electrons. So not only is it harder because I'm taking away electrons from a bad ratio to begin with, but now I'm taking electrons away from something that's 1 entire energy level closer to the nucleus. So this nucleus can pull way stronger onto my electrons. As a result, the energy to make those electrons come off is 7,730 kilojoules per mole. So you see this huge jump. It escalates quickly. So you'll see 736, 1445, and then all of a sudden like 7,000 kilojoules here. That is what you see in all elements. So what happens is it goes up a little bit every electron that you take away, and then you get a huge jump once you start to take away core electrons. So these two here are valence electrons. This third electron is a core electron, and core electrons are really, really hard to remove because they have, like I said, 1 whole energy level closer for their position, and they have a very generally higher proton to electron ratio. So you will see that. Okay. Hopefully that makes sense when we're talking about successive ionization energies. A question that they might ask you is something like, they'll show you the ionization energies on the table and ask you how many electrons it has, and where you see the big jump, that is where you should see the number of valence electrons. So in this case, after the first 2, those are easy. So it means you have 2 valence electrons. Okay, I'm going to go over one example question with you to show you kind of how I would answer that, and then we'll be done with this video. So example number 3 says, would you expect the first ionization energy of potassium to be greater than, less than, or equal to rubidium? And justify your answer. Okay, so what we need to do is we need to find our elements on our periodic table. In the case of these questions, just like with ionic radius, or not ionic radius, I'm sorry, atomic radius, they're probably only going to ask you to talk about things that are either next to each other or top to bottom. So if we find potassium and rubidium, we have two things that are in the same family. If we follow the trend, potassium is smaller than rubidium in its size, and thus it's also smaller in its ionization energies. And anytime we're talking about things in a family, it has to do with the number of shells that are there. So that's what we need to discuss. So our first ionization energy of potassium is going to be greater than rubidium because it's closer, those electrons are closer to the nucleus. So we've got to talk about that. So I'm going to say the first ionization energy of potassium is larger than rubidium. This is because potassium has fewer shells of electrons than rubidium. When the first electron is taken away from potassium, it is taken away from a shell that is closer to the nucleus. This makes it harder and therefore requires more energy to remove. Okay. So we would talk something like this. As I'm reading through this, I'm kind of doing these on the fly. This is kind of vague, so it says this makes it harder. I would say this makes, let's change this. This makes the pull from the nucleus stronger and therefore requires more energy to remove. So hopefully you can kind of see as I'm going through this, when I reply, I sometimes have to revise my answers too. So again, this makes it harder. What do you mean harder? Well, it means that it's makes the pull from the nucleus stronger, therefore it's harder and takes more energy to remove. So don't be afraid to revise your answers as you're going through these. Make them as specific as possible without writing me a novel, and we should be good to go. If you find yourself struggling with ionization energy, please make sure that you get a hold of me and we'll get things cleared up. Otherwise, good luck on your homework, and we'll catch you up with electron affinity next.